Okay, we will learn about Chapter 2, Determinants. So in this chapter, we will consider 3 sections. Section 1, Determinant of a matrix. And Section 2, we will learn about properties of determinants. And Section 3 for some additional topics and applications for determinants. The first part of Section 1, we consider the motivation of introducing a determinant. We know that later, we know determinant of an n by n matrix A, we write it as DETA, can tell us whether A is non-singular or not. And also, we will find determinant of A will provide another way to compute the inverse matrix of A. First, this is a 1 by 1 case, if the matrix is only 1 by 1. Then, if A is a 1 by 1 matrix, we know A will have a multiplicative inverse if and only if A does not equal to 0. Okay? Thus, if we define the determinant of A by this way, just equals A, then A will be non-singular if and only if determinant of A does not equal to 0. Now we see the 2 by 2 matrices. Here, we have these 2 by 2 matrices. A defined like this, A11, A12, A21, A22, which is non-singular. We know that A will be non-singular if and only if it is a row equivalent to the identity matrix. So first case, we consider the general case. A11 does not equal to 0. Then for this matrix A, we can do the Gaussian elimination. We're using the first row as the pivotal row and the A11 entry, this one to be the pivot element. Then we do Gaussian elimination. We eliminate this entry to be 0. We will get this matrix in row echelon form. And you can see that A is non-singular if and only if A11 times this term does not equal to 0. Here, A11, we already know it is non-zero, so this one is non-singular if and only if this term A11 times A22 minus A21 times A12 does not equal to 0. Okay, some special case, if A11 equals 0, we can switch the 2 rows of A. The resulting matrix will be row equivalent to identity matrix if and only if A21 times A12 does not equal to 0. So you can see that A can be transformed to this row echelon form. And this matrix A is non-singular if and only if A21 times A12 does not equal to 0. And because A11 equals 0, you can check that this one also is equivalent to this term, does not equal to 0, because here A11 equals 0. And now we consider 3 by 3 matrices. We know that A will be non-singular if and only if it is row equivalent to identity matrix. So if A11 does not equal to 0, we write A here, and then using the first row as the pivotal row and the first 1-1 entry, this 1-1 entry as a pivot element. Then we do the Gaussian elimination. We try to transform A to row echelon form, and we first using this A11 to eliminate all the other entries in the first column to be 0, and we will get this matrix. Okay, and to see if this matrix can be transformed equivalently to the identity matrix, you can only check this submatrix, this 2 by 2 submatrix. Okay, and we know that the resulting matrix will be row equivalent to I if and only if this one does not equal to 0. And here, this is a 2 by 2 matrix. We know already that this one does not equal to 0 if and only if this the main diagonal entries, the multiplication minus the multiplication of the off diagonal entries does not equal to 0. So later, by simple computation, you can see the 3 by 3 matrix, the determinant does not equal to 0, means this summation for 6 terms does not equal to 0. Okay, so A will be non-singular if and only if determinant of A does not equal to 0. Okay, for 3 by 3 matrix, there are also some special cases. If A11 equals 0, this means the first row, the first entry is 0, then it cannot be the pivot element. In this case, if A21 does not equal to 0, then we try to change the order of the first row and the second row. Now A21 will be the pivot element. And by direct computation, you will find that A is row equivalent to I to the identity matrix if and only if these 3 terms does not equal to 0. And this is the same as 1 with A11 equals 0, because when A11 equals 0, here we will find this one 0, this one 0, and they are equivalent, okay? And another special case is that A11 equals A21 equals 0. This is when A31 does not equal to 0, then we know that A is row equivalent to the identity matrix if and only if this term does not equal to 0. And this is also the same with 1, with this expression 1 here, with A11 equals A21 equals 0. Okay, and another special case, if A11 equals A21 equals A31 equals 0, then this matrix A cannot be row equivalent to the identity matrix, and this matrix must be singular, so we don't need to care about it. Okay, so in order to assign a value to the matrix, which can indicate whether this matrix is non-singular or not, so we define the determinant. For 2 by 2 matrix, A defined in this way, we can define its determinant in terms of the 2 1 by 1 matrices. See, let us denote M11 equal this one, and this matrix, submatrix, is formed from A by deleting its first row and first column. So by deleting its first row and first column, you will get this M11, this submatrix, okay? And similarly, we can denote M12, this matrix, by deleting its first row and second column. So delete its first row and second column, you will get this submatrix, A21. And the determinant of A can be expressed in this form. Before we know, determinant of A can be defined as A11 times A22, the multiplication of main diagonal entries minus the multiplication of off-diagonal entries, A12 times A21. So here, and using the M11 and M12 we define, then determinant of A can be further written as A11 times a determinant of M11 minus A12 times the determinant of M12. So this means for 2 by 2 matrices, the determinants can be defined using the determinants of 1 by 1 matrices. Okay. Now we consider the definition for determinants of 3 by 3 matrix. We can rewrite the equation in this form. So determinant of A just equals A11 times this term minus A12 times this term plus A13 times this term. And in the bracket, the first term, you can just write as the determinant of a 2 by 2 matrix, see? Just by deleting the first row and the first column of this matrix A, you calculate this determinant of submatrix M11. And the second bracket, this term, just equals determinant of M12. And the third term in this bracket just equals the determinant of M13. So M13 means you're deleting the first row and the third column of this matrix, and you calculate this determinant of this 2 by 2 matrix. One thing we should be careful is that here we have the sign here. So the first term is positive. The second term here is we have a negative sign here, and for the third term is a positive sign.